Good morning, everyone. Find a seat, please. People standing in the back, could you please look forward? Those who have seats next to them, raise your hand high so that they can see. And you should feel quite free to come forward and scramble over people's knees to get to the center. They know that's going to happen when they sit on the aisles. Thank you. Right, we're going to do some visualizations today. There's some here. I see a couple there. All right, settle down, please. Announcements, same as last time. Thank you for all those people who are keeping their hands up. But please take advantage of all that. Seats. Thank you. Same as last time. Homework is due tomorrow. You get an extra point for turning it in today. The routine is the same every week. Small group tutoring sessions have been announced on Piazza. If you feel that it might help you, then please take advantage of it. They're filling up. Okay. I want to pick up where we left off last time. What we had done last time was we had gone through a series of table operations on columns and rows, and then we had taken a data set from the census, and we were just about to start looking at the data and interpreting it when time was up. So let's review where we were. As we said last time, the census is a every 10-year thing. Every 10 years, the U.S. government counts the number of people in the United States. And it's not citizens or anything, it's just how many people are in the United States. And the reason for doing that is the Constitution says that there are apportionment, representation, and federal funds and so on are connected with the number of people in each state. This is a massive undertaking. It's quite difficult, but it's done every 10 years, and also in between those 10-year periods, there are estimates made every year so that people are prepared for what might come up in the next census, and governments and so on can make policy based on more current data than data from 10 years ago. We saw a data set that we had loaded from the census, and there was a sex column which had some codes, and then there was an age column with age in years, and I'll just go over. The sex column had a numerical code for male, female, and the estimates were done at a particular time. The population estimates were done at a particular time of the year. The columns also had some aggregated data. So the sex column, when you see a code of 0, it was everybody. And the remarkable age of 999 years is actually not 999 years at all. It was everybody of all ages. So these, instead of writing male and female or everyone, they were using numeric codes. This is for storage efficiency, and also because you don't want to be typing words all the time. Very often, numerical codes are used. That doesn't mean they're actually numbers. I'll come to that later. So values in a column have the same type. You know that they're arrays. The point that we're trying to make here at the end is age 12 is actually 12 years old. That's a kid. You can imagine that. Age 999 is not an age. It's a number here as far as the computer is concerned, but it's not an age. And when we interpret data in tables, we have to keep things like that in mind. And where do you know what's going on, like what these codes mean? You have to read the documentation provided by the people who made the table. And so there's a link to that at the bottom there. So what I'd like to do is I'd like to get started by reviewing where we were. So there was census data. The census provides data in this file right here, and we read it into a table called full, and that has a sex column, an age column, and various population columns, from which we selected 4 columns into a partial table, which we called partial. This thing had 306 rows, and it had sex, age, the estimate in 2010 and the estimate in 2014 of the total population, and it's broken down by at each age group and each label for sex. We did not like these long column labels, and so we did some relabeling. We relabeled that long pop estimate 2010 to be just 2010, and then we were too lazy to even type in pop estimate 2014, so we just used the column index there. We relabeled column 3 to be column 2014, and we took a look at that. And now you have a table that is a little easier to comprehend and work with, and so that's what we're going to start doing. I think last time we had also decided that we didn't like looking at large numbers and not knowing how big they were, so we used number formatter, and now you can see that you have essentially 4 million people in each of those cells. Every age group, 4 million people. And these are the little tiny ones, age 0 through 9 that you can see. But then the table continues. We took a look at the age labels, and there was 999, everybody put together, everybody of all ages put together there. Sex was 1 male, 2 female, 0, everybody. And so what we're going to do now is, because it is extremely disconcerting to work with ages of 999, we're going to do some further reduction of this table. I'd like you to look at age 100. Age 100 there isn't exactly 100 years, it's 100 plus. Everybody, 100 plus, was lumped in there, and that's why the numbers are bigger. And we'll look at them again. But so even 100 isn't 100 years old, it's 100 plus, 999 is everybody. So now, I will take one short pause for questions. This is where we were. This is exactly where we were, I think, last time. So the first thing we'll do is we will get rid of the 999. So I'll create a table called No 999, where you take this table and you take the rows where the age column index 1 are below 999. And I do that, and I don't see anything because that's an assignment statement. That's fine. I'm not going to run the same thing twice. What I'm going to do is I'm going to extract a table for everybody. So from this, every row where sex is equal to 0, and then we'll make a table for the guys. And for the girls and the women. And so we'll create those 3 tables. And we take a look at table called females, and so that's, okay. At every age 0 through 100, you have the number of females in the years 2010 and the year 2014, and I look at that sex column. Well, this is the table of females. Every single one of them is going to be a 2. That's rather boring. So we should not be carrying around a column that just has all 2s in it. So how about we go back? We haven't messed with no 99, so we're just going to drop column 0 here for all of them. Okay. Now, actually, we have some data there that are interesting to look at. So we have the females, and we have the males as well, and I have a question for you. So you can see that there's slight differences in how many females there are at each age group. For example, there are more 9-year-olds than tiny infants. You see that? Yeah? So among the females, which age do you think is the most populous? Talk to your friends and neighbors. You can't tell that from here. You just have to guess based on what you know. All right, since everybody's guessing, somebody call out a guess. 60. Sorry? 50? 60. Somebody guesses 60. Roughly why? Baby boom. All right, that's a good guess. Others? Other candidates? Yes? Above 100. All right, because there's lots of ages in there. More? 37, because?
Because it's like, they're closer to baby boomers, but they haven't died.
Closer to baby boomers, they haven't died yet. Okay, great. So then, morbid as it might seem, that is exactly the kind of thing you have to think about, yes?
About 20.
About 20, why?
Because that would be about when the generation above the millennials is stopping being the major segment of producing kids, since millennials are notoriously not producing kids.
Oh, wow. So now we're looking at millennials. There's a lot of them, but they don't have a lot of kids. And so maybe their kids are all over 20. So now maybe let's look at the 20-year-olds, and there's a lot of them. So shall we actually look? Let's actually look. What? No. I already know that 100 is bigger than 99. This is silly. Okay. So I'm just going to look at the 2014 population. So who said 60? Yeah, I think you're the closest. Yes? All right. So there's more in 2014. There were more 54, 53-year-old women than anything else. 20. Somebody said 20s. You had 20s. Somebody else had 20s. Yeah. So you guys weren't doing so badly. But you can see they're all sort of in the 50s and in the 20s, which is interesting. It's quite interesting to see whether the picture is the same for the men. No, not the same for the men. Most common for men is 23. There is a 54. You can see, but it's way down. All right? And so these very dry numbers are telling a story. They're telling a story that guys' lives are genuinely different from women's lives, and also their biologies are different. So what we're going to do now is we're going to take a look a little more carefully at these data, and maybe what we can do is create one table with both genders. So let's just call it population 2014. So I'm just going to look at the year 2014, and you can, if you want, you can change all this later. So for age, I can pick any one of these first columns. Okay, so look at the number of males compared to the number of females at these different age groups. Do you notice something? Consistently fewer little girls than boys of the same age. Look at age 0. Those are the kids just born. The proportion of females is not 50%. This has long been the case, and there's some biology that it is not clear to me is completely well understood. The proportion, a baby born is slightly less likely to be a female than male. And at all of these ages, the proportion of females is slightly less. Why don't we just work out what the proportion is, and then we'll take a look at what that looks like across all the ages that we can't see. So we'll create an array called % females. Okay, so we will convert these numbers to a % of the total. Yeah? How do I find the total? Well, it's the sum of these two. So we will take y dot column and not select? Because it's an array. I want to do arithmetic with it. I don't want to just visualize in a table. I want to do some arithmetic. Okay, so I got to take it and add it and if I do that, I will get a fraction, so why don't I convert that into a % by multiplying by 100? And then we create a new table called counts and percents, which is our old table, POP 2014. So just about 49% female throughout in these age groups. Okay, so now what does this look like for all the other age groups? Of course, we could turn the table over and sort by age in descending order and take a look, but it's a good idea to draw a picture. This is just crying out for us to draw a picture, and so what we will do is we will now draw some line graphs. These are plots, and so I will take the table dot plot produces a line graph, and we will plot the age on the horizontal axis, so the columns are age, and I will plot % female on the vertical. That is interesting. You start out, proportion female is just below 50% by about 40 males and females in equal proportions, and what happens to the senior citizens? At the higher ages, you're seeing quite substantially more females than males. So that is an interesting observation from this graph, and we'll look at it a little more carefully. I just want to go over the call. So if you have a table of data and you want to draw a line plot of one column versus another, then table.plot. You can use two arguments. The first one will represent the horizontal axis, and the second one will represent the vertical. All right, so what would be nice is to see to look at the males and females separately and possibly on the same graph if possible. So let's take a look at POP 2014 again. These are counts, not percents. So what we're going to do is we're going to take We're going to draw two plots on the same graph. These are called overlaid plots. And so I'm going to plot the males versus age and the females versus age. And to do that, I just have to specify which is the x-axis. Then every single other column will be plotted as the y-axis. So there'll be a separate graph for every single other column. These are counts. Number of people in each age group, and the blue graph represents the males, and the gold graph represents the females. So this is another way of visualizing what we just did. Before I do that, any questions about the call? If your data set, so our data set had everything numerical. There was a column of ages, and then there were numbers. If you had a column of names as well, then plot would be unhappy. So select the things that you want to plot, and then work with a table like that. All right, so you can see what we saw before. That is, up to the age of about 40, there are fewer females than males. Around 40, it overlaps, and then by the end, there are more females than males. And, there's some fluctuation. The numbers aren't always the same. There's sort of moving all about, except there's a plummet here. Right? That's unusual. Just a very sharp drop. And so what we're going to do is we're going to see what was happening at those ages. And these ages are right about here. So why don't we look at... Okay, take a look at those numbers, see what you spot. Do you see the plummet? The very sharp drop, one age to the next. Where is it? Which age? 67, right? If you look from 67 to 68, you have, it's 1.8 million versus 1.3 million. Something happened there, right? And there is something else going on, 71 to 72, there's, something noticeable going on there. And so what would be very nice to see is who are those people? And so what we're going to do is we're going to figure out, well, when were they born? Right, so if somebody is 67 in the year 2014, these are only from 2014, then you can figure out when they were born by subtracting their age from 2014. And so we are going to do 2014 minus. We don't need to do all of them, I don't think. How about we do 67? Okay, before we run this, somebody explain to me what's going to happen. 2014 is a number I'm subtracting off what type of object? It's an array. And so what is that operation going to do? Element-wise, one element at a time, right? So it is going to return what? It's going to evaluate to what? An array. And the first element of that array is going to be 2014 minus 67. The second element of the array is going to be 2014 minus 68, and so on. And what's the purpose of doing this? It's to find out what year these people were born in. So take a look at that. 1942 to about 1947. What was going on in the United States in those years? War, right? So Pearl Harbor was in 1941. And so if you look at the oldest people, the 72-year-olds, that's what you're seeing there. And then there's some number of births. And so the war ends around here. Everybody gets home. It takes a while to have a baby. And then in 1947, suddenly there's a lot of babies. And that's pretty much what you're seeing here. And so the point of this is not just to show you the method calls, but to notice that something as slightly prosaic as census data can tell stories if you look at them and ask questions. And so we encourage you, when you look at any data set, to ask why, to notice unusual blips, and to ask why they are. And sometimes you learn something quite interesting. Okay. We had one data set that had everybody in it. What we're going to look, this is now looking at the change from 2010 to 2014. So is somebody watching YouTube? And if you insist on doing that, it's called earbuds. Thank you. All right. So this column represents the change in population between 2010 and 2014, and no surprise there, the biggest change was at 67 years old, because the people 67 years old in 2014 those are not the same people, right? How old were they in 2010? Sorry? 63, right? You have a jump there. And so what I'd like you to do is, I'm not going to dwell on this particular column now. What you're noticing is that what I'd like you to do as an exercise at home is to see how you can reconcile this with what we just said, that the 67-year-olds, there was a jump there. This is another way of looking at the same element. What I'd like to do is actually I would like to look at growth rates, because I have heard from core staff that people are unhappy about growth rates. And so instead of looking just at absolute change, I would like to look at rate of change here. And before I do that, I'd like to ask your patience. I want to take you through a little discussion of what growth rates are and how that calculation comes about. And then we're going to use it. I've heard from numerous staff that growth rates caused unhappiness. So, okay, let's see if we can be a little less unhappy. So a rate you can think of as a percent or a proportion. So there's some growth rate. Don't worry about the letters. Just think of it as 3%. If a population, you start at a certain point, you have some initial value, and you end up at a certain point after a specified period of time, then you have grown. And you have grown, we say, at a certain rate. And what we're going to do is figure out what that means. Okay, so after one time period, just assume that you start with something that we're calling x. You can take it to be 100 if you wish. After one time period, you have your x, plus you have 3% of x. Okay? So that's the total population that you have, and a little bit of pulling out the x says that after one period, you have what you started with initially times 1 plus the growth. So what I'd like to do is just fix the growth rate to be 3% in our heads for an example. If I start out with 1,000 people, then what I have at the end of 1,000 at the end of one period is 1,000 people times 1.03. Right? And that is the base of the calculation. At every period, you see what am I starting with now, and then you multiply that by 1 plus the rate. And so therefore, you agree? At the second period, you are starting out with where you were at the end of the first period. And so you were at x times 1 plus g. So 1,000 times 1.03. So you take that number and you multiply that again by 1.03. Questions about this line? This is the crucial line and everything else is just, okay, so now we're going to do it for a bunch of periods. So for the third period, I'm going to take this as my starting point because that's how many people I have now, and I'm going to multiply it by another 1 plus g, and so I'll get a 1 plus g cubed, and so on. And so if you have t, this is t for time period. If you have t periods, then at the end of t periods, you'll have your initial starting point, which is x, and then your 1 plus your growth rate, 1.03, to the power of your time periods. And so what does this do? This says, if you know your initial point, that is how many people you had at the start, that's x, and you know the growth rate, right? You know that you're going to be increasing at 3% every year, then this is what helps you figure out where you're going to end up. This is what helps you figure out what your ending point is going to be. So this is what I call the forwards direction calculation. I know where I'm starting, I know what the rate's going to be, I figure out where I'm going to end up. Very often, we know where we're starting, we know where we ended up, and the question that comes up is, what did the rate have to be to make this possible? That is what I call the backwards calculation. I know the start, I know the end, I don't know the rate, but maybe I can figure out what did the rate have to be to get from this particular start to this particular end. And so for that, what you have to do is you basically have to solve for g in this equation. And so the next thing that I'm going to write down, if you don't like solving for stuff, just tune out. But if you do like solving for stuff, then you can see that this is just, I'm just going backwards. You will never have to do this in this class. There are some people in the room who find it more reassuring if they know where stuff came from, so I'm just telling you where it comes from. And so this back calculation is what leads to the formula that you have been using in your labs for growth rate, which is to figure out what rate could have got you from initial x to ending y. You take ending divided by initial, raise it to this funny power, which is 1 over the time periods, and take the whole thing and subtract off 1. That's where that thing comes from. If we ask you to do growth rates in exams, we will provide you with the formula. You don't have to worry about it. Right? But I want you should have some sense of where these things come from, and this is a little description of where it comes from. So 2 minutes for questions. Yeah.
Isn't that the cumulative growth rate from the beginning and not just the growth rate from the previous period?
This is the annual, so just think of periods as years. This is the annual growth rate that would, if you compounded, would have led you from X to Y in T periods. It is a per year rate. Okay, so we're just going to apply this thing. You've done it before in lab. I just want to make sure that we're okay with doing this. Okay, so here. So we're going from 2010 to 2014, so it's going to be everyone. Why did I do that? Dot column 2 divided by dot column 1. Why did I do that? I'm not done yet, but why did I do this? That's taking the end value dividing by the initial value that we said we had to do. And then what we have to do to this? We have to raise it to a power. Yep. 1 over how many time periods were there? If we're looking for an annual growth rate, how many time periods were there? Excuse me. Now you can see. 4. There were 4 time periods. And after having done all that, we have to subtract off 1 from this. And what we're going to do is we're going to look at sort. Okay, I'm going to shut up, look at that. See what needs to change. See what that's telling you. There's something a little alarming about that. Okay, what have we done here that isn't working out correctly? You know, I'm not happy about this at all. Where did I make everyone? Yeah, just a moment. Let me just come back to where I was. Yes. There's a parenthesis issue. I'm just trying to recompute the... it's this. Thank you. Okay, so we were all unhappy because of why? Because the minus signs. Yes? The populations are increasing, you can't have minuses. Something was wrong in that calculation. And because of this thing doesn't fix itself going back up, I had to recalculate the entire table and come back down, and I didn't want to do run all above. So, okay, let's try this. Much better. Much better. Positive growth rate, because you can see from 2010 to 2014 the numbers are higher. Yep? Okay, all of these are around 0.07, 0.06. Where's the highest rate of growth? The very, 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 very senior people. And if you compare to like the 1960s, the people in those age groups, like 99, 100, and the people who are 100 and up, they have grown by almost 75%. There's a very significant growth in that age group, and this is, a very vivid picture of the graying of America. Okay. So what I'd like to do today is we've had a lot of discussion of wars, people getting old, and so on and so forth, and at your age group, it's a little depressing. So I want to look at something a little more and light, but yes. No, we're looking at annual growth rate. Per year. Rate per year. Yeah, annual rate. Okay. Let's quickly summarize. Actually, not summarize. There's language that we just use. I want it on slides so that you know that it's actually statistical terminology and not just some terms that we're making up here. Types of data. You know that everything in the column should have the same type and be comparable in some way. We are now bringing that in because you've had ages of 23 and 54 and a so-called age of 999, and you shouldn't be working with that 999 at the same time as the 23 and 54. Okay, numerical. Numerical measurements, they're on the real line necessarily. They're ordered. 53 is bigger than 21. Differences matter, right? There is it's a length or a time period difference. Categorical is like if you are looking at favorite colors. So categories, red, blue, green. Each value is from a fixed inventory. Just means that you have a total set of 5 colors, and each person will give you one of those 5 colors. May or may not have an ordering. So here's some categorical data. You do a little rating of something, and you are not satisfied, somewhat satisfied, very satisfied. Those are categories, but they have a natural ordering. And so some categories may be ordered, but red, blue, green is not necessarily ordered. Categories are the same or different. Well, so are numbers. But the point is you can't have fractional differences in between, right? You're either in this category or you're in that. And we will choose our categories so that we don't have overlaps. Okay, so this is now so-called numerical data. Just because the data are numbers doesn't mean the variable is numerical. So your sex code had number 0, 1, 2, but you can't subtract and take averages of those numbers. It doesn't make sense. They're just labels, and you could just as well have called them red, blue, and green. And so one of the things that happens is, there's a big discussion as to whether course evaluations of teachers, how they should be summarized. So at the end of the term, you have to do a course evaluation. And there's would you rate the effectiveness of this course? And there's like a 1 through 5 scale. Yep. So you're giving back a number, and it sure looks like a number, but it's a category. Right? It's your rating of that person. Are you somewhat satisfied, very satisfied? Basically, it's a category. And then what we get back are averages of those numbers, and we're looking at that going, I'm not really very sure what this average means. Because after all, one person's 4 and somebody else's 4 might mean quite different things, right? And in any case, those numbers don't make any sense. So let's just keep this in mind. And so the variable sex is still categorical, even though the numbers were used for categories. Okay, so we know how to do line plots. We're now going to quickly see another kind of plot, and I hope to get you to something interesting. We have just about enough time. Okay. So you will have noticed that I'm really bad at typing. Like, really bad at typing, especially in a lecture in front of 700 people. It just doesn't work. So when the function calls are simple and there's really not much new going on, you will often find that I've already populated the notebook. I will take you through what is typed there, and then we'll hit return, so that you don't have to go through me going back and correcting my own mistakes over and over again. Okay? Okay, so what we're going to do is there's a table called actors. We are going to take a look at these people. There are 50 actors in this table, and about 2015, they were the people that had... Okay, so now let me explain what the columns are. So there's the name of the actor. Total gross, that's not the amount of money that the actor makes. That's the total amount made by the movies that the actor was in. And that is in millions of dollars. Then there's the number of movies that actor has been in. The average per movie is, among that actor's movies, what was the average amount made by the movies? And the number one movie is this actor was in a bunch of movies. One of them had the highest grossed amount. Which one was that? And that's there. And then I think it's I think, what did that one gross? Their highest grossing movie. What did that one gross? And so there's a table with the 50 highest ones in about 2015, and you can see most of them are guys. There's a few women as well on the list. Okay, so what I would like to do is I would like to draw a scatter diagram. What I'm going to look at is, we're going to take a look at this diagram, and then we're going to see exactly what it's doing. This is called a scatter. It is not a line plot. On the horizontal axis, we're going to have number of movies, and on the vertical axis, we're going to have the total amount grossed by the movie. This is a scatter of points, like a cloud. It's often called a cloud. Each point represents one actor. And it's basically like plotting points on an XY grid. On the horizontal axis, you have number of movies, and on the vertical, you have the total amount grossed. Okay, so who was the top here? It was Harrison Ford. 41 movies, top grossing was about there. So can we find Harrison Ford here? 41, top grossing, this one. Agreed? Okay, I'd like you to take a look at that scatter. What that is showing is called positive association. The more movies, in general, the more total amount of money. Right? You can see that there is a trend. The two variables are associated. There is some relation between them. Association was the word that we had in our second lecture when we started out. This is positive association. No surprise. The more movies, the more total amount made. So what we're going to do now is we are going to look at a different scatter diagram, number of movies versus the average amount made per movie. Again, every point is going to be an actor. Woo, very different. Very different. Negative association. So there's a point for every actor, and what you're seeing in this is that the more movies those actors made, on average, the less those movies made. So you can see the negative association, and there is one point that is just screaming at you. Yes? You see this? Screaming at you. Shall we find out who that is? Because this person is the boss of this diagram. Small number of movies and through the roof average gross. Okay, so tell me if you think that is a good call. Actors are where the average per movie above 400. Look good? Yes? All right. Anthony Daniels. Anthony Daniels. Don't look at me like, who's Anthony Daniels? What do you mean? Anthony Daniels is the boss of this diagram. Small number of movies, a ton of money per movie. All right. What is the data science lesson? Pay attention to what's being measured. You're not measuring what the actor makes. You're measuring what the movies make. This actor is only in the Star Wars franchise. Every single one is a blockbuster. On average, through the roof. Okay. Guys, I want to say something about Friday. Friday, people go through the following calculation. I've done my lab. It's Friday. I got other stuff. I don't need to come. Here's what I'm going to say. This particular Friday is on histograms. People make this calculation every term, and they look at it and go, oh, that's a bar graph, I understand. We have found that this topic causes trouble on homeworks, labs, and especially the midterm. Please show up.